Welcome. So we'll be solving another question on bending stresses in a beam. It says a rectangular beam 300 mm deep is simply supported over a span of 4 meters. Determine the uniformly distributed load per meter which the beam may carry if the bending stresses should not exceed 120 Newton per millimeter square. So take your take your moment of inertia to be 8 times 10 to the power of 6 mm to the power of 4. Alright, so I just decided to draw the beam carrying the uniform distributed load only without the rectangular section, because we are just given the depth. We don't know the width, that is the wideness of the section, or you can also call it the base. All right, so here is our given data. We are given the depth, the length is 4, the maximum stress is 120, and then the moment of inertia is also given as well. So the first thing we are going to do here is you are going to recall carefully that under the application of Flegeral formula, if we have a simple supported beam that carry a uniform distributed load, if we want to calculate the maximum bending moment, we know that the formula for that is WL square divided by 8. All right, so we are going to start with the maximum bending moment of this beam. So that's WL square divided by 8. All right, so since it is W we want to calculate, so we'll just leave this W there, and then we'll substitute for our length. Our length is 4, so we are going to have this to be W times 4 square divided by 8, which is going to be 16 W divided by 8, so which is going to give us what? 2 W, but it's going to be Newton per what? Newton per meter. All right, and of course, if we want to take it to millimeter, we are going to multiply by 1000, which is going to give us 2000 W Newton per millimeter. All right, so that's our maximum bending moment. All right, so the next thing we are going to calculate here is our sectional modulus. All right, we know that our sectional modulus, denoted by Z, is equals to what? Is equals to I divided by what? Y max. Our Y max is, for a rectangular section, is D divided by 2. That is the depth divided by 2. All right, so we can therefore say that our Y max is going to be equals to, what is our depth? Our depth is 300. So 300 divided by 2. So this is going to give us 150 mm. All right, so we can therefore say our sectional modulus will be equals to moment of inertia, which is 8 times 10 to the power of 6 divided by our Y mass, which is 150. All right, so if we are going to have this. All right, so again, you are going to recall, and what will be the unit of this our sectional modulus? The unit of our sectional modulus is always in mm to the power of 3. So it's going to be mm to the power of 3. All right, so the next thing, you need to recall carefully from the relationship between from the Flegeral equation, that we said that our maximum bending moment is equals to maximum stress times our sectional formula, our sectional modulus. I've already proved this formula for us in our video on sectional modulus, so you can watch that. You are going to see how we derive this. All right, so the next thing is to substitute. So here we are going to have 2000 to be equals to the maximum stress is 120, then times our sectional modulus is 8, times this is supposed to be 2000 W. All right, so 8 times 10 to the power of 6 divided by what? 150. All right, so if you make W the subject, our W will be equals to 120 multiplied by 8 multiplied by 10 to the power of 6 divided by 2000 multiplied by 150. So our final answer here is going to give us what? 3,200. 3,200 Newton per meter. So this is going to be the solution to this question. I believe we understand. It is very, very simple and it is well explained. Mind you, if today is your first time of coming across our content, please don't forget to share this with your colleagues who might be in need of this, and don't forget to click the subscribe button and stay tuned for more interesting content like this. Thanks.